In this lecture, I want to talk about linear time invariant systems and the discrete time Fourier transform. So in this lecture, we will talk again about LTI systems and take some examples on how to find the frequency response and also the output of an LTI system using the DTFT. So typically we will be characterizing an LTI system using a linear constant coefficient difference equation, or what we will refer to as an LCCDE. So here let's take an example. So typically the input is X, so this is the LTI system. So this is the LTI system, and the input is X and the output is Y of n and X of n. And the LCCDE describes how the input and the relationship between the input and the output. And the question here is to find the frequency response h of ej omega of this LTI system and to find its impulse response. Now to do this, we go back to the LCCDE and then we take the DTFT on both sides. So here the DTFT of y of n is y of ej omega minus 3 by 4. So the DTFT of yn minus 1 here is a shifted version of the DTFT of y, and it's shifted by 1 unit. So it's going to be equal to minus 3/4 e minus j omega y of ej omega plus 1 over 8. And here the signal is shifted by 2 steps, so it's going to be 1 over 8 e minus 2j omega y of ej omega 2x of ej omega. And all I have to do now is find the frequency response here is actually, so h of ej omega is by definition y of ej omega divided by x of ej omega. So it's the output divided by the input. So this is gonna give me 2 divided by 1 minus 3/4 e minus j omega plus 1/8 e minus 2j omega, which is the expression that is here. So this is the frequency response of the LTI system. Now to find the impulse response, I have to invert this function. And to invert this function, we need to find its poles and then do partial fraction expansion, and that's what I want to do on the next slide. So you find the poles of the denominator, and you can easily find them by solving quadratic equation, and you can find that h of ejw has 2 poles, one equal to 1/2 and one equal to 1/4. And then you can write it under this form, and now you can do the partial fraction expansion, where you can write that h of ejw equal to some constant divided by 1 minus 1/2 e minus j omega plus some other constant divided by the other factor, and then you can find these constants a and b by using the method that you know by now. So here I'm just giving you the result, but you should actually check it that is correct. And once I have it under this form, you can easily identify that these guys here are the geometric series, right? So one starting at 1/2, or one with a factor of 1/2, and one with a factor that is 1/4, and you have the constant 4 here and 2 here. And this is how you basically recover your signal, which is here the impulse response of the LTI filter. So now that we have the impulse response and the frequency response, we have a new question. Suppose that the input to this filter is x of n, which is 1 over 4 to the n u of n. Find the corresponding output y of n. We know that the output y of the LTI system in the frequency domain is the convolution of the input with the frequency response. So we know that y of ej omega is equal to h of ej omega times x of ej omega, and I have each one of these the expression of each one of these terms. So the impulse response is this part here, and x of ej omega, which is 1 over 4 nun, is 1 minus 1 over 4 e minus j omega, which is this part. So when I simplify things, I'm going to get that y of ej omega to be 2 divided by 1 minus 1 half e minus j omega 1 minus 1 fourth e minus j omega square. Now, using partial fraction expansion, you need one term that has 1 minus 1 4 e minus j omega, and one term that has 1 minus 1 4 e minus j omega, which is here. But since 1 fourth is a pole with multiplicity 2, so we have to add also one term that is 1 minus 1 4 e minus j omega square, and this is how we can do the partial fraction expansion. Now, we use the same method we learned before to find these coefficients, and then you can find them equal to -4, -2, and 8. And please do these calculations at home and double check these values. Now that I have the DTFT of the output that is written this way, I can try to find the output in the time domain y of n by inverting each one of these terms. And if I do that, what I will get is the following. So you can see here that this term, let's call it in yellow here, this term here is easy because it's geometric series with which is 1 over 4 u of n. So let me add here. This is u of n here. And this term here in green is this guy here. Oh, actually there's u of n here, so I don't need this guy. I didn't notice that the u of n is outside. So now what would be maybe a little bit, will take a little bit of time to figure it out, is this guy here in red. And this looks like the derivative of one of these guys here. So because it has square here. And then you can apply the differentiation formula to get this value here. So n of xn, if you remember, we studied this property that n of xn, what would be the DTFT of it. So again, here you have n plus 1, so you have to make sure, I mean, there are a little bit of details that needs to be worked out, but again, this is something that you should double check at home. So this way you can get the output in the time domain. So two things that we learned today through an example is how to find the frequency response, which is the output divided by the input, and how to use and then you can use this frequency response to get the impulse response by going back to the time domain, and also you can use convolution to get a relationship between the input and the output of an LTI system.